students, welcome to the YouTube video lectures for the Fundamental of Physics course. If you are not subscribed, please subscribe my channel, click for the notification, like it if you like, leave some comment and share it with your friends so that everyone should get the benefit and I will get the feedback. Today, chapter number 21, alternating current circuits and electromagnetic, waves, alternating current AC. You see, we have this electromagnetic radiation. Electromagnetic radiations, they are fluctuating electric field E and magnetic field B. They are perpendicular to each other and perpendicular to the direction of travel. They are traveling to the right. So we have a big electromagnetic spectrum, and ranging from the physical, for example, I'm writing here, you can see easily due to the visible region of the electromagnetic radiation. So we are able to see the objects around us with the help of the visible portion of the light. And similarly, when we are using TV or radio programs, so radio waves, they carry out TV programs and the radio programs to you. And as you see this title slide of this chapter, Arecibo, the largest telescope in the world at Puerto Rico, it gathers electromagnetic radiations to create images of different objects in the space like Milky Way galaxy. So the topics we will be discussing today are, AC circuits, so resistors in AC circuits. So what happens when you connect a resistor with AC source, and then what happens when you connect a capacitor with the AC source. This is capacitor, and then we will see the behavior of an inductor in AC circuit. So inductor L, AC source, right, alternating current source. RLC series circuit. Then we will combine all these circuit elements, okay, and we will connect it with the AC source and we will get some interesting results. And then finally the resonance in RLC series circuit. So I will explain it in detail, don't worry. Now, you see, whenever you turn on your TV or other electric appliances, you call on AC, you call on alternating current to operate those appliances like TV, for example. And before going to the alternating current, the difference between DC and AC, you see, if you have, this is the time and this is the magnitude of the voltage or the current. For example, this is, I say, okay, 10 volts DC. Okay, this is positive, this is 0, this is positive, this is negative. So this is constant, almost constant over the time. It does not change, it remains constant, the value of voltage or the current. So this is the DC waveform, okay, direct current. And if you connect, DC source with some load, bulb or anything, which I call the resistor. So, for example, if you connect with it a bulb, right, and current flows through it, right? I say, okay, for example, I say let 2 ampere current is flowing through it, and this is 10 volt, for example. So power calculation is easier in DC, right? Voltage multiplied by the current. Voltage 10 to, so 20 watt is the electrical power. But if you look at AC now, alternating current, like this one, for example, you see this is 0, this is positive side, this is negative side, and you know, if I say this is 10 volt positive, you see this is positive and this side negative, right? So why we call it AC? AC means alternating current. Alternating means changing, right? The AC voltage at the current, it reverses its direction many times a second. For example, if you have 60 hertz, then it is changing, you know, for example, you see, from here up to here, this is one time period complete. So this is positive side during, you know, the first half of the time period. After that, it becomes negative. It continues positive, negative, positive, negative. So this is what we say alternating current. And for the power calculation with AC circuits, we need effective value of voltage and the current. You see, as you see that average, if we take the average over a cycle, it will be 0, because we have positive, for example, 10 volt, negative 10 volt equals 0. So the average of the voltage and the current over a cycle is 0. But yes, by taking the square of the voltage or the square of the current will solve the problem for power calculation, right? Because if you have power VI, so V is equal to IR multiplied by this I, so it is equal to I square R, and even you have power is equal to V square or R. So even for the negative values, you get positive value. Okay, even for the negative value, you will get the positive value. So all values above, so it will not affect your power calculation. Now, how we do it, in fact, you know, actually we need root mean square values, RMS values, right? And RMS value is really important in power calculation, and in you know, the electrical engineering, it's really very important. So what is the method to calculate the RMS? For example, you have this waveform. You see, it goes to the positive, so Vmax is 10 volt, and it goes to 0, again minus 10, and then it continues. So what is the method? If we divide all the waveforms in equal sections, 5 here, 5 here, 5 here, plus 5 minus, even you can have many other. So what do? We take the voltage values, equal sections, and then we take the square of all those values. If, for example, you get all this voltage, and this is the square of that, then what you do, you add all divided by the total number of your readings. So this will give you the VRMS. VRMS root mean square is equal to sum of, you know, your values square, this one, okay, or we take it the square root. That's why we call it root mean square. You get the idea? We take the voltage, equal sections, divide it. Even you can take some values from the half, right? For example, if I take 1, 2, 3, 4 and 5, square these values and divide by 5, I will get the RMS. Just to cut it short, you know, I can write 0 is the minimum value, for example, and the maximum is, you know, Vmax. This is Vmax. Maximum voltage square over 2, take the under root, you will get Vmax over under root 2. If you use the calculator, you will get 0.707 Vmax. Okay, Vmax will be somewhere over here. VRMS, sorry. This is Vmax, this is VRMS. Okay, now if you have, for example, Vmax 10, so you will get 0.707, 7.07 volt. So 10 volt is the maximum and 7 volt will be VRMS, root mean square value. What is root mean square value? It's an effective value of AC quantities, whether it is voltage or the current, which needs to be considered for power calculation. Okay? So similarly, you have this rule for the voltage. You can have the same rule for the current. Root mean square value for the current I max over 2, which is the same 0.707 I max. These two values you can use it. All right. This is the notation we use throughout AC circuits, especially in this chapter, that if you have instantaneous value for the voltage delta V, instantaneous current I, maximum value as you have seen, V max, I max, or delta V max and delta I max, whatever you need, RMS value for the voltage, and this is for the current. All right. Now, as I told you, as I promised you in the beginning, that we'll be discussing today, you see, we have and by the way, I will give you for the RMS values separate lecture I will upload, don't worry, in a few days, based on the calculus integration, how we can calculate the RMS, what is the method. Okay, I will upload it shortly. Now, first of all, you see, we will study today looking into the characteristic of a circuit containing two things. One is the source of the voltage, okay, source of EMF or the alternating current, and the second one is the load, the component, electrical component. By the way, right now we have a resistor. Okay, so this is the first part, then we will go for capacitor and inductor and then all together. So before going into detail, you might have seen in chapter number 13 waves and vibrations. You see, you studied there simple harmonic motion, and that was a sinusoidal wave, sine wave for example, that was equal to xm, which was the amplitude in fact, okay, sine of theta or sine of omega t. Theta is equal to omega t, or omega is further equal to 2 pi f, so you can write, x is equal to x max, which is the amplitude AV, right? And in case of waves and vibrations, chapter 13, you remember, sine of omega is equal to 2 pi ft. T is the time, f is the frequency. Okay, this is the maximum value, this is the maximum value. Okay, and x is instantaneous value at any time. For example, here, okay, here, but this is the maximum x from the equilibrium position. Okay, so similarly, we are writing in place of position x, we are writing current at the voltage. Right now, writing the voltage. Okay, here maximum voltage, remaining is the same. Okay, right. Now, you see, whenever we are changing frequency of the AC source, it does not affect the resistance of this ordinary resistor, right? Its resistance remains constant, its behavior is linear. So what does it mean? It means that the voltage, okay, this is the current, you see, this is the current waveform, and this is the voltage waveform. Okay, voltage across R, current through resistor R. Okay, so you see both waveform for the current and for the voltage, they reach their maximum value at the same time. This is time axis. Okay, even the negative value highest, they reach at the same time, and similarly here. So we say that voltage across resistor R and the current through resistor R, okay, is the same. Phase angle is 0. They are in phase. The current and the voltage are in phase, mean they reach their maximum values and the minimum values, even the zero value, they reach at the same time. So they are in phase. You can write here even, this is voltage, current, and this is voltage. They are in phase. Keep in mind, because the behavior of capacitor and inductor will be changing. Okay, now we have to calculate some parameters even in the example we would see, and let's discuss a few points here. First of all, IRMS we have already finished once we calculated the root mean square values for the current and the voltage in the last slides. I max over under 2, this one, this is the root mean square value for the current, this is the rule. Okay, and this is the voltage for root mean square value for the voltage. This is what we already done. And our resistor impedes, it opposes the, what is the resistance? Resistance is the ability of a component like a resistor to offer some resistance, to block, to try to stop some of the current flowing through the circuit. That's the resistance. So it opposes. So you see, we have Ohm's law. Okay, this is Ohm's law. Voltage is equal to I multiplied by the resistor R. So we can calculate VRMS in this way also. These are different rules. It depends what is given about to find out in the coming examples. This equation is also true for the maximum values. So this is for RMS, Ohm's law. So same Ohm's law is valid for V is equal to IR, V is equal to IR. Here you have RMS, here you have maximum. So V sub R max means voltage across resistor R maximum value is equal to I max multiplied by R. Right. Now we have next example. AC voltage source has an output given to you. Okay, and right, R is given to you. Where is R? This is R resistor. It's given to you. This is delta V given to you. Okay, this is the voltage at any instant of time. You have to find out what VRMS and IRMS. These two things you have to find out. All right. So we have seen that VRMS. We have just finished that delta V max over under root 2. Delta V max given? Not given. So first, let's find out delta V max. Okay. Now you have this equation. Okay. 2 sine 2 pi ft. Okay, this is given to you, and we have delta V is equal to delta V max sine 2 pi ft, which is the standard, the function for the voltage. You remember we did this one here. It's here. Delta V is equal to delta V max sine 2 pi ft. Okay, so now if you compare these two, you see del V sine 2 pi ft in black, just so that you can identify. In black color I wrote. So comparing these two equations, I get delta V max is equal to this much. So it implies delta V max is equal to volt. I would use this value over here. So I would get the RMS 141 volt. Right? Now IRMS I need. This is done. Now IRMS. I don't have I max, so what I do, I use Ohm's law, which says V is equal to I multiplied by R. So and I will be equal to V over R. Okay, VRMS over R. So VRMS we just finished. R is given to you. So you would get IRMS in amperes. You would get 1.41. Okay, this is the voltage RMS, this is the current R. That's it, finished. All right. Next, as I told you that one by one we'll be going to discuss. Now we have second element. First we just finished resistor connected with AC source. Now capacitor. All right. You see, you have right. Okay. You might have seen, different type of capacitors in your labs. Okay. And this is before we had resistor. Now we have connected capacitor. It's a symbol for the capacitor. Okay. Okay, this is the AC source. The same waveform, the wave function for the voltage. Right. Now, the behavior, very important thing, please note. The behavior of inductor and capacitor, right now we are talking about the capacitor, so behavior of the capacitor changes with changing frequency of the source, right? Resistor, there was no change. Now, the behavior changes mean, you know that every electrical and electronic component, it offers some resistance in the circuit. Same thing capacitor will be doing, it will offer some resistance to the current flow. But since its behavior is different from the ordinary resistor, so we cannot call it resistor. Of course, it will be a sort of resistance with the same unit ohm, but we give it a different name. We give it a name reactance. Why? Because its behavior is different from ordinary resistor. Please keep in mind. So the effective resistance of the capacitor in alternating current circuit is measured by a quantity called capacitive reactance. C for capacitive, X is the symbol for reactance. So the rule is 1 divided by 2 pi Fc. What is C? C is the capacitance. Okay, in the unit of farad. F is the frequency. In the unit of hertz. And Xc is the capacitive reactance. Of course, in the unit of ohm. You see the equation 1 divided by. So if you increase frequency, capacitance, reactance will decrease. Again, if you increase capacitance C, it will decrease. So capacitive reactance decreases with increasing frequency and increasing capacitance, and vice versa. Right. The same thing we did with the resistor, same parameters we need. We need voltage RMS, V sub RMS, this is C, mean the voltage across capacitor is equal to I multiplied by V is equal to I multiplied by R. As I told you, we don't call it resistance R, we change this R with reactance symbol. Okay, please keep in mind. Now, phasing, or are these two voltage and current, they are in phase or not? In resistor they were in phase, right? Now if you look here, you see this is current waveform, this is voltage waveform. Okay, now it starts from here and completes one cycle, one time period over here. It's the maximum, at the maximum. Voltage starts from here, it reaches after one time period at 0. You see the voltage across the capacitor lags behind, means it's behind. So who's leading? Current is leading. So current is leading in this case. So keep in mind, we will use this data in RLC series circuit again. Okay, so the voltage lags behind. So if this is current, this is the voltage. So 90-degree lagging behind. Okay, in case of resistor, this was the case. They were in the same direction. Okay, current and voltage for R, for resistor. But now for capacitor, they are out of phase, 90 degree. But current is leading and voltage is lagging behind, it's coming after that, like here. Okay. Right. Let's solve related example for capacitor and AC circuit. Right. This is microfarad, so farad delivers capacitance. So this is capacitance connected to the terminals of AC generator with RMS and frequency. Right? So you have to calculate capacitive reactance XC and IRMS. Okay? So you are given what is given? VRMS 1.50 10⁻²volt. Capacitance is given 8 times 10 raised to power micro minus 6 farad, and frequency 60 hertz. Right. We know that XC is equal to 1/2 pi FC. 60 C, you would get capacitive reactance 332 ohm. Right? Now you need IRMS. We have Ohm's law, okay, which says V is equal to IR. So you need I is equal to V divided by R. So I RMS or R, resistor. But now we don't call it resistor in case of the capacitor because its behavior is changing. We're changing the frequency. We already named it what? XC. Okay, this one here. So VRMS, you have it, yes. XC you just finished. So you get to be RMS. How much? 0.452. Right? Okay. I believe keep it up to here. So I'm coming shortly for the remaining, second part of this lecture. The next upload will be. Okay. Thank you very much, and we'll keep watching